Hello, everyone. Welcome to the third seismic lecture. Today, we are going to talk about networks again, a bit more advanced than the previous time. So it's networks 2 for today. And I'll start today's lecture with a bit of recapturing what we discussed in the previous lecture, and then I'll proceed to today's lecture, which is basically to cover a bit of what you are requested to do on the exercises for the next before the next lecture. I always like clearing my command window and all the variables from the workspace before starting a new task. So everything is clear now and we can start straight away. I prepared the code as I did in the previous lecture, and I can share that with you at the end of today's lecture. Just to recap what we did last time, we'll create a biograph with 10 nodes. I've got 10 nodes here, and play a bit with amending the biograph so we can remember what we did last time. So as said, we are creating a biograph with 10 nodes. So we need to have a variable holding the nodes number. It's going to be 10. And then we are going to create a matrix from which we are going to use later on to create the biograph. So I'm naming the matrix here random matrix because it will include random variables, random numbers using the function rand. We discussed this in the previous lecture, so I'm not presenting them here. You remember the structure that I used last time. At the end of the code of each section, I'm presenting all the functions, the MATLAB functions that were used, and adding a link there so you can read more yourself, or adding a few comments here. I'll come to that one in a second. So I'm now creating a random matrix, naming it randmat. And as you can see, if I open it, it's a 10 by 10 matrix because we mentioned 10 nodes are needed for that one. It's a 10 by 10 matrix with random numbers between 0 and 1. In order to create the biograph, we will need some edges that will connect the nodes with each other. In order not to have too many edges, I'm gonna select a fraction from that matrix to be zeros or ones. And in order to create that matrix, I'm using a logical function here, the smaller. So what we are doing here, we are selecting only a fraction of the whole matrix, which will be below 0.1. The value is going to be below 0.1. So instead of having the word fract here, I could have had 0.1. However, we set this value into a variable. It's always better to set values into variable because if you've got too many lines of code, it's easier to just change one variable instead of going line by line and changing one by one the values. So here we've got the fraction of connections to be realized, and they are gonna be only those that keep the value lower than 0.1. So if I run this line of code, we are selecting from the randmat, the matrix, only those values that are less than 0.1. So if I run the rand matrix, can you spot somewhere which is gonna be less? Yeah, here for example, 0.04. It's less than 0.1. So I expect that in row the value in row 8 and column 9 to be 1, while the rest of them are gonna be 0. I mean, for example, that one 0.3, which is above 0.1. And let's run the code and see what we created here. So if I open the random math fraction, the fraction of random matrix is again a 10 by 10. It's a logical matrix this time because this is what we requested to have. And we requested a logical matrix by having this sign here, and I'm gonna come back to this in a second to explain what this is. So we can see one by one the 10 by 10 matrix, and we can see in row 8 and column 9, as spotted earlier, is the number 1, while the rest are zeros apart from the ones here who are numbers less than 0.1. Instead of using this sign here, which is the smaller than, we could have used the LT, lower than. That's a function in MATLAB, and you can check it yourself as well by clicking on this link. And the syntax for, I mean, when you are comparing two values, you then create a logical array or a logical matrix. It depends if it was an array or a matrix at the beginning. As you can see here, it's the word logical. So it's a 10 by 10 logical matrix. The syntax is very straightforward. A less than B, using that sign there, or the LT lower than A comma B, which are the two that we are comparing. Okay, and if you go into this link there at the bottom, you are gonna see the other functions that are for comparison reasons. The equal to, for that one you can use either the EQ and then in brackets A and B, A comma B, or you can use the double equal sign, that one. Then G, which stands for greater or equal, for that one. Then G T, which is just greater than this signal, this sign, sorry. The LE, less and equal, or the okay, the LT as said, which is the less than here, and the not equal NE, it's the not equal sign. So this is what we did here, and you can try and explore yourselves on your own time. Now we are creating the biograph of the matrix that we just created using the logical matrix. So where it's 0, we are going to have 10 nodes. Where there's 0, there is not going to be any edge connecting those two nodes. 2 with 1, for example, or 3 with 1, or 4 with 2. They are not going to be connected. And where there's a number 1, there is a connection. So node 5 and 4 are connected. Let's run the biograph. So at the first one, we are creating a biograph object, and we are assigning it to variable v. So you can see here the variable v of the biograph. And in order to view this biograph object, we need to use the view function as learned last time, view of variable v. And here it is. Here we have a biograph. As you can see, there's a connection between node 4 and node 5, as we mentioned, and all the other nodes that had an 1 in the appropriate position within the matrix. So, for example, node 2 has no connections at all. There are no edges with any of the other nodes. That means for node 2 there was no one in the either here or here, and there are no connections between those. Here I'm playing a bit with the layout of the biograph. I'm changing this to equilibrium. What I mentioned below is that if you go to the layout type, if you go to the biograph, basically in the MathWorks website, you are gonna see the layout type value. There are three different types: the hierarchical, the radial, and the equilibrium one. The default one is the hierarchical, so there is no need to mention it. It's gonna be the one that you can see here. That's the hierarchical. But if we need to amend it to a radial one or the equilibrium one, we need to mention it. And let's do it. Sorry. So by changing the layout type to be equal to equilibrium and run it, we will have the equilibrium one. So it's not hierarchical anymore. And at the next step, I'm trying to make them the nodes a bit bigger, so I'm increasing the font size in order to be easier to view them. You'll have this code at the end of the lecture, so you can play around and familiarize yourselves. Hopefully you've done that in the previous lecture, but repetition is what makes you understand the topics much better. As you can see here, node 2, there is no connection with any of the other nodes, as mentioned earlier. And also what we discussed last time is that we can amend the biograph function using by clicking on it, right click, and then node properties, and we can amend here whatever we want to amend. For example, make the line around it pink. You can see it's pink now. Or you can just drag and drop it to a different place. Anyway, clearing this up. Hopefully it's understandable for you now. And I'm now proceeding to the next section where we are gonna deal with the exercises that you will have to do for this week. So here what we are gonna do is to use the two functions that you can download from the website, from the Seismic website. Yeah, it's in the Seismic website under the networks topic. You can see the function files that you are gonna use is the adjacent matrix in SymBio, and then average clustering coefficient. So I've got them here. We are not going to discuss them now, but you are going to use them in order to proceed to the exercises. We are going to discuss them in a second, I mean. So initially here you need to create an undirected network and get the clustering coefficients. By saying undirected network, it has all of its edges bidirectional. And that means that the adjacent matrix is symmetric. I've added here some comments for you. So when you read the code, you understand the topic and what we are doing here. Talking about clustering coefficients, the clustering coefficient is a measure of the degree to which the nodes in a graph tends to cluster together, to be close to each other. You are going to understand this better when we visualize it in a second. So let's start. We are creating a variable with 100, the number 100 as a value. This is going to be used for the coefficients. So we are going to have 100 coefficients within that network. And by using the function, as you can see here, here it's let's create a new one so I can understand, because you haven't seen a function in the past, right? Okay, so functions are being used for instead of having to write a piece of code again and again and again within the same script, you just create, I mean, if you need to run the same thing again and again, you just create a function where you place the whole part of the code within it. As you can see here, the average clustering coefficient is a bit more. Instead of writing this part of code again and again and again each time, you just create this function file and then you just recall it in a single line of code, right? So the way of creating the function is, as you can see here, a new function. And the coding of the function, the structure of the function coding is, as you can see here. So in brackets, or it could not be brackets, it could just be a single value. If we didn't have that one, if it was just the output argument one, there is no need to have the brackets, okay? But if we are having two and more, you need to have the brackets. And so at the beginning, you mention the output arguments that the function is gonna create, and then equals to the name of the function. That's how we are gonna call it. That's how we are gonna call it in the main script. The name of the function, that one is untitled, but as you can see here, we named it adjacent matrix sim, or average clustering coefficient, as you can see here. And then in brackets, square brackets here and brackets here, it's the input argument 1, 2, 3, 10, 100, or whatever the number of the input argument is. And then we always start the function with the word function here and end it with the word end. Whatever is in between those lines is the script that is gonna run when we call the function, okay? So here, okay, it doesn't do anything here. The output is gonna be equal to the input. So whatever values we give here, by running that function, the output is gonna be the same number or the same value or whatever. So here, as you can see, by running the adjacent matrix function, it creates a symmetric matrix with randomly assigned zeros and ones and zeros on the diagonal. And as is mentioned here, half of the entries will be ones. That's on average. And the reason of doing this is, as said, we need to create the undirected network. And the piece of code that is going to be run is that one here, the one that is in between the function and end, the words function and end. So coming back to the main file now, we are running the adjacent matrix function that we just created here. Well, it was created for yourselves and you can download it from the CINMIC website. And we are saying the input that we are giving it is the value that the variable k is holding, so 100. And the output is going to be the output that is mentioned here. So it's going to take the variable k, is going to run, create random variables using that number, and the output, it's the one that is going to be here. So running this part of code, we've created 100 by 100 matrix where there's one and zeros. And this matrix is undirected. It's the adjacency matrix there is symmetric. If we want to see the degrees, we need to sum all the ones within the matrix called A. And that's what we do here. And as you can see, the variable named out degree gave us the sum of each of the 100 columns. So column 1 has 54 ones, column 2 has 50 ones, column 7 has 45 ones. The rest are zeros. So the 55 in column 7, 55 are zeros and 45 are ones. And that's because using the sum function, it always sums by column. I think I added it here, or not at all, because I think we used it in the previous in the previous lecture. And then I'm creating a histogram of the out degree, the one that we just created, to see the sums, to see the coefficients. And as you can see, all these are coefficients. There are, for example, 56 coefficients with number 50, or yeah, 6 instances of 50. 56, there are 7, and so on. The more there are 13 of number 49. And if we want to see the average degree out of all these instances, we just use the mean function, which is the average. It's going to create the average value of the array. So by running this piece of code, the degree average here is 49.9. It's the average of all the values within this variable, the out degree variable. And then in terms to see the clustering coefficient, basically these are the questions that you are being asked here in the exercise. Calculate the clustering coefficients and the average clustering coefficient. using that function. The function can be downloaded. It's the one you've seen earlier, and you just use this function here. Basically, you need to read the function file. There's a great explanation here on what the inputs are, what the outputs are, and there's an example. There's an example on how to use this function, and that's what we do here. So we call the function with inputs the A matrix and outputs A, C, C, and C. And as it can be read in the function file, ACC is the average clustering coefficient of the input graph, basically the input matrix, and C is the local clustering coefficient for each of the nodes here. So I'm running this part of code. I've created the ACC and the C, and if we need to see the clustering coefficient for each of the nodes, it's here. So here are the coefficients for each of the 100 nodes here that we've got. And the ACC is the average of them, which is 0.5029. If we want to see the coefficient, that's the next question, to plot the clustering coefficient distribution using the histogram. So the exercise helps you on how to plot the clustering coefficient. You are using the histogram function. We've discussed about histogram in the previous, did we? I think we discussed it in the previous lecture, but here it is again. You just call it using the function histogram, and you can just use the matrix. So let me do this. You can just use the matrix that you are gonna use to plot the histogram, or you can add the number of the bins of the histogram instead of creating the full variety of the input values. Let's say 100 here is gonna create is gonna add them into bins of a lower number. Let's say here we are using number 20, so it's, instead of having 20 bars into that chart, instead of having 100, it's going to have just 20. You are clustering them into a smaller number. So by just using the histogram, see, let's basically, yeah, here's a histogram with all the, yeah, so 20 is a bit too much. Maybe if we add 3 just to see it. So we've got the histogram here. As you can see, these are the coefficients, and there are 40 coefficients within that difference from 0.5 to 0.51, or there are 20 coefficients, 51 to 52. If we set the number of the bins, you now see that I grouped them into 3 bins, and now we only have 3 bins here. Or we can use number 20, for example, and have 20 bins. So make it more detailed. We can get more details instead of having, let's say, I don't know, 14 plus 12 plus 15. here, instead of having them all together in one bin, we are now having 3 bins here. And you might be wondering what is the subplot here and the figure here, etc. So each time we are creating a new figure, instead of just running it on itself, we might need to save it into a variable. So we can call it f equals figure1. And what this is gonna create, what the function figure is gonna create, is a figure, a clear figure, empty. I mean, an empty figure. And then having that on the side, let me, having that on the side, we can work on it. If I just click on histogram, it's gonna add the histogram on this figure. Okay, and then now we are talking about subplot. Having the subplot is to create 2, 3, 4, or whatever number of subplots within that plot. So if I click on figure and create, sorry, if I create a new figure here and click on subplot 2, 1, 1, 2 is the number of columns, 1 is, the number of rows, 1 is the number of columns. So by running this, I created, and the third one is which one we are accessing now. So here subplot 211 is accessing the subplot in row with 2 rows, 1 column, and the first one on top. If I was using that one, it was gonna be 2 rows, 1 column, the second one, the one on the bottom. We are gonna see that in a second. Or maybe, as you can see here, I use that code and it's the first one on top. Or if I was gonna use that code, it created the second one on the bottom. And I've got another function here. It's the bar. It creates a bar chart. I've got the link here if you want to investigate further. And it will add the bar chart with all the 100 coefficients, and then, all the 100 nodes at the bottom, and the number, the coefficient of each node here. So if I run all the code together, we created this nice plot which has the bar chart on top and the histogram on the bottom with the 20 bins to investigate the coefficients of each of the nodes here and all together here. You can check those links on your own time. And we are gonna proceed because we don't have enough time left. We are gonna proceed to the second exercise here, where you are being asked to download the P information, network information, using, let me share my screen here, using the Reactome pathway finder. So you just have to go into the Reactome website. It's reactome.org. Click on the pathway browser here. And then, as the exercise is mentioning, you need to make sure that you are looking a pathway for Homo sapiens. You can, you've got other options here, but we are using the Homo sapiens one. This is the one we need, and you are gonna look for the pentose phosphate pathway, clicking on search, And then you've got here pentosephosphate pathways, the triple P pathway. It finds it for you. And what you need to do is, as you can see at the bottom, there's the description, molecules, structure, etc. You need to click on the downloads and download the file that you are gonna be using. The file that we need to download is the SBML here. So you click on the first icon here and save it where you need to access it. I've got a folder named networks 2, and the name of the uh, pathway that we are downloading is RHSA 71336. I've already downloaded it. That's why it gives me the 01 here. And as you can see, the format is an SBML file. So the extension is SBML. And you just click save. I'm not gonna do it here now because I already downloaded it. And you can see it, it's already here, 71336. So what you need to do in the exercise is to import the model into MATLAB and examine the number of species and reactions. Okay, so there's a network with nodes and reactions and edges that react with each other. What I will be doing here is to use the SBML import. This is the function to import the model into MATLAB. You can click on this link here to access more information about the SBML import. And the way of doing it is adding in brackets the name of the model that you of the file that you need to access, which is that one here. I just typed it there. It's very important to add the extension as well, .sbml. In the past, it used to be XML, I think, but at the moment is SBML. I mean, in previous versions, it was before 2018, it was XML. So if your file here is an XML one, you just need to use the XML here as well. But don't bother with it. Now you will be using only SBML. And it's important to add the single quotes here around the name of the file that you need to access. So I'm running the SBML import function to import this file, and I'm gonna assign it into a variable called my model. This is what we are doing in this piece of code. So if we look at my model, there is it's a sim biology model. I forgot to mention that it's important to install the sim biology toolbox on your MATLAB before trying to work on this exercise. And the way to install the sim biology toolbox, if it's not installed, I mentioned it here at the beginning of the code. For you, it's easier now to do it. So what you have to do is to go to the home tab, and then in the add-ons, select the get add-on. And from the window that is going to open, you just have to search for the sim biology add-on here. Click search. It will find it for you. You can see for me it's installed. If it's not installed for yourselves, you can just click on it and then go to get. There is gonna be a get button here. Add button there, and you will add it you will add the toolbox into your MATLAB. Talking about toolboxes, there are, if you are not familiar with toolboxes, they include a variety of functions that are being used for a group of specific functions. For example, here it's used for the sim biology one. There are different toolboxes. You can have a look at the add-ons on the window that opens on your free time anyway. So what we did is to import this file that we just downloaded from the Reactome website, and we imported it into MATLAB, and we added it into the variable with name my model. In order to count the number of species of this, basically when we add it, if I don't use the semicolon there to suppress the output, it will give me the output at the command window as well. So you can see there are 20 reactions within the triple P pathway model, and there are 42 species. So there are 42 species which react with each other 20 times. I mean, there are 20 reactions within them. You will understand in a few minutes what I'm trying to say. But here, by using the size of my model.species, so we are accessing the species within the my model variable here, element here, and we are counting the size of it. And we are assigning this number, which is going to count the size, into the variable named number of species. By running this part of code, as you can see here, number of species 42, and we assigned it as well into the number of species, as you can see here, which is what we saw earlier in the output of the SBML import function. The same way, we can do the number of reactions. We are assigning the size of my model.reactions, so we are accessing the reactions within the my model. We are getting its size, assigning it to the number of reactions variable, and you can see there are 20 variables here. If we just mention the my model.species and access it, it will give us all the species that are included in this model. As you can see here, we've got the TK18 dimer, GA3P, they are all in the cytosol, ATP, AMP, etc. You can see them on your free time. And it also includes the reactions. You can see there are 20 reactions as mentioned earlier. These are the reactions of the species that we saw above. So how do these species react with each other? And you can see here the SH7P reacts with GA3P and TKT dimer to give, these are the products of this equation. Okay, and so on in the rest of them. As you can see, we need to get the adjacency matrix of this model. We need to get the adjacency matrix of this model, and there's a function. Okay. We are doing this because it asks you to extract the adjacency matrix for the network and the node names. And then view it using images. See, we are gonna come back to this in a few minutes. So first of all, to get the adjacency matrix, there's a function named get adjacency matrix, one word. And this is a MATLAB function. This is not a function that we created. It's already there in the Symbio toolbox. So you just use the get adjacency matrix. You can see the link. You can investigate further yourselves. And by saying adjacency matrix, I added here a comment on what this is. It's a square matrix, again, used to represent a finite graph. So it's a matrix that used to create a graph, and the elements of the matrix indicate whether pairs of vertices are adjacent or not in the graph. So it's the spatial distribution within the graph. Are they all together? Are they adjacent to each other? Or are they sporadically distributed? So by running the code get adjacency matrix, the input is going to be the my model. The output is going to be the model network. I'm going to show you how this looks like, and the headings. The headings is the names of the nodes as the exercise was asking. So I'm going to run this part of the code, and I'm going to access the model. First of all, the headings. As you can see here, we've got all the names of we've got all the names of the species and reactions. Species on top, so we should have 42 species. Yep. And then from 43, line 43 to 62, there are 20 reactions. So in the same file, you've got the reactions along with the species. And the model network, it is a network. It is a sparse matrix, which just shows you the interactions. So 43, 1, 44, I mean, line 44, which, and 2, etc. Or 11 with 47, and so on, as you can see here. These are the lines. This is an index. So if we talk about 43 and 1, that means if we go to the headings, it's line 43 includes the 43, sorry, includes this reaction, and 1 is the TKT dimer. So there's correlation with those two. If we want to, as the exercise asks, to view this network, how does it look like? We use the image C function, and it's very straightforward. You just type images C and the name of the network, of the sparse network. And I'm mentioning this sparse network because in a second we are gonna show it in a full matrix, how it looks like. But yeah, images C is a function. You can see the link here. You can investigate further yourself. And yeah, using the images C. As seen, by the way, it stands for scaled. And as you can see, we've got the 40 species on the lower left side of the graph, and the reactions on the top right corner of the graph. As you can see, it's 42 here, and then from 43, as we mentioned earlier, there are the reactions until 62, up to 62. Yeah, I've added the comment here that the matrix rows are species, and the reaction, and then there are reaction nodes. So 1 to 42 are the species, 43 to 62 are the reactants, the reactions, and the connections between species to reaction are the top right corner, and the connection between the reactions to species are the bottom left corner in the image you saw earlier. In terms of the number of nodes, if we need to count them, we just use the size of the model as we did earlier. There are 62 nodes, 40 of which are 42 of which are the species, and the reactions are the rest. And the number of edges, we just need to get the sum of the model network, and you can see there 114 edges, 114 connections between the 62 nodes. And in the next exercise or question, it asks you to do something to find what happens to G6P in the triple P network, and it gives you a hint on how to work here, and that's what we are doing. But basically, before we move there, I'm gonna convert the sparse into a full matrix. It's what I mentioned earlier, but I'm gonna show you what's the sparse matrix and what's a full one. A full one is 0 and 1s, as you are used to. I mean, these are the matrices that we used to use in the previous exercises, so you're familiar with them. And instead of having the sparse one, we can convert it into a full matrix. A sparse matrix a full matrix takes too much space, and that's why people are using the sparse ones. I've got the link for the full function here, so you can see it yourself. And I've added the comment. The sparse matrix is a matrix which contains very few non-zero elements. Instead of using the full one, which wastes a lot of space to represent the matrix, we just use the sparse matrix. If it was 100 by 100, containing only 10 non-zero elements, you are going to have a 100 by 100 matrix, and they are going to be all zeros apart from 10. 10 are going to be ones. So what we, sorry. So that's why we are using the sparse matrix here. But just for you to see the difference, we are gonna create the full matrix as well, and we are gonna call it model network full. So if I click on the model network full, we've got the 62 by 62. It's full of zeros, and there are a few ones here. And the ones are that many that you can see here, and we counted them earlier, and we found them to be 114. That means there are 114 ones within this sparse matrix. If we need to check the sum over the rows of the matrix. I mean, using the sum function, we count the sum over the rows by default. Sorry, we over the columns by default. If we need to, and this is counting an in degree. If we want to count the out degree, we need the sum over the rows. And in order to count the sum over the rows, we will need to add this quote there at the end of the variable named model network full. And what this does is to transpose the matrix. You know what transposing is, right? Great. So by adding this single quote there, we transpose the matrix, and therefore the sum that we are gonna create is the sum over the rows. By getting the sum over the rows, and then let me visualize it using the histogram function. This is what it looks like. And to find okay, here I had an example from previous exercises, but you are not asked to be doing this. So I'm not gonna go through that one at the moment. You are asked in the exercise to see what happens into the cytosolic G6P in the triple P network, and mention to which substance is converted. So what I will be doing is to okay, manual work. You have to go to the headings and find where the G6P is. It's in 32 row, and then look for the G6P in the reactions and see to what is converted. This is the manual work that you can do. However, what I'm doing here is to use the okay, I'm not doing it now, but using the regex function, I'm figuring out in the index of the G6P. Let's do it actually. So you can see that they are all empty apart from 32. As you can see, the 32 that we found earlier in the headings, that it includes the G6P. I'm not doing it here because it's a bit complex for you now. And even here, what does this symbol means is basically to matches it matches a word starting with M here, or the G6P and space that I added in my code at the beginning of the text. You will see this in the anchor section in the regex function if you click on this link and investigate more on yourself, but you don't have to bother at the moment. So we know that it's number 32 in the headings. We've got G6P cytosol. So what we need to find is in the model network full, the one that we converted it into zeros and ones. Oh, sorry. So in line 32, they are all zeros, apart from somewhere there should be a one. So if we look manually to find the one, here it is. So there's a one in column 54, and line 32. That means that their G6P is included in the reaction found in the line 54. So we need to go to the headings here and see what's included in 54. As you can see, in the G6P is included here, and we can see to what is 54 here, to what it's being converted here. Instead of doing it manually, I'm just using this line of code here, where I'm finding the index of the model of within the model network full, the matrix with zeros and ones, line 32, and which column does it contain the number one. So running this code, it just gives me number 54, and then I'm looking for this the name of the value on this section in the headings. So headings 54, or because I assigned number 54 in G6P reaction in PPP variable, that's the variable name. I'm just running the headings of the to find this variable, the number 54, and it gives me the answer here. It's D-glucono 1.5 lactone 6-phosphate. This is what the G6P is converted. And what you can do is then to look for that one if it's further being converted into anything else down the line. If you have any questions, I guess you can use the forum in the website. And thank you, people, for your attention and for your time. Very